then it could happen that you will be asked to calculate what is the input signal after you calculate correlation with such a normalized function. And then what actually will be different, that instead of 1, you will get some constant. So just keep in mind that it could happen that in general, I mean, there are no restrictions that all basis functions has to be normalized. It's, of course, it simplifies calculations, but I mean, even if it's not unnormalized, then it's not tragedy. It's just should take into account this and write your solution. Okay, I think there is a question. Do we need to take the noise into the calculation? Yes, we need. Yes, we do, or yes, we need. But we do it in the next step. We do it step by step, because if we do everything at one moment, then it will be overwhelming, and then it will be difficult to understand what happens actually. So yes, of course, we have noise, and we take it into account, but we take it independently. But yeah, in the next part. So far, we assume that what happens if we don't have any noise, just ideal situation, if we have only signal S, and then what we see as output after this processing, if we have only signal part. And what we see actually is that the output will be the following. Output will be 2EB under square root times B0. And what it means? It means that output will be equal to 0 if you transmit 0, if your transmit bit equals to 0, and then you see 2EB under square root if you transmit 1, if your bit equals to 1. And somehow, again, you could look and say like, oh, well, it's like the same quantity that we had before. I mean, nothing special. I mean, it was already given. It was already given above. Yeah, it already was written at 2EB. But this is you shouldn't be. No, I don't know this word, but I want to say that you should be. You should distinguish these two situations, because before we have shown a signal space diagram, but because our basis function is orthonormal, it has unit energy. Because of this fact, after processing, you get exactly the same quantity. But if you wouldn't have orthonormal reference signal, then you will get different result. And then it's not necessary. But yeah, because we used all this all conditions that we posed by ourselves, that unit basis function, orthogonality, and so on and so forth, then we get very nice result. But only because of this. In general, you could get scaled values. Okay, and actually, it also gives us answer to the next part of this question, which says that or where we need to describe how the decision for S1T and S2T is made based on y1. So I show you axis with voltage with output voltage. Output voltage. This is voltage. Actually, we have only one axis. We don't have two. We have axis y1. Let's say t. But yeah, no. Let's say y1 without t. And we have actually two possible values. We have 0 and we have 2EB under square. This is another possible value that we receive. But this is at receiver side. It's not signal space diagram. even it looks like it is, that it's voltage at 0.1. And you have two possible values. When you transmit B0 equals to 0, then you get 1 point. When you B0 equals to 1, you get another point. And then the question here is the following: where you need to put the threshold in order, or in general, where you need to put threshold during detection? And the answer, it depends. It depends what's your criteria. And there are many different, there are three ways how to determine threshold. Maximum likelihood, Neyman-Pierce detector, and third one, I don't remember. But anyway, in our course, we assume very simplified case that we say that symbols independent statistically and likelihood to observe any of them the same for all symbols. And as a result, our strategy will be to place threshold in the middle between possible voltages. So this is our strategy for this course. We just take value in the middle, and this it will be our threshold. And if you take this value, if you try to find this value for this example, it will be, I mean, I can simply write this maximum value divided by 2, yeah? And I write what will be the result after you divide by 2. It will be EB over 2 under square. This is the result that we get, that this is the value of this threshold. Yeah, it's not the all answer, it's only threshold. It is the value for threshold. And now we need to specify how we make detection. I think there was a question from Nandish. Can you explain once again about orthogonality of this question? I mean, there is nothing to explain about orthogonality. I just said that because we use orthonormal basis functions, but for this specific example, we have only one basis function. But nonetheless, because we use orthonormal basis functions, many things will be simplified. And when you write the received signal after processing, typically it's just the same value as in signal space diagram because of all these measures that we do, taking into account orthogonality and orthonormality. Okay, and now let's say that the estimate of our signal S hat of t, we actually do the following. It's too long. So for S1 of t, or we say that our estimate equals to S1 of t, for when voltage or value of Y1 will be lower or equal than what? Than our threshold, EB over 2. If this value will be below our threshold, then we say that, okay, it's signal S1. And if this output value exceeds our threshold, then we say, oh, it's mostly likely that it's S2. This is how we do detection. We just compare our output voltage with specific threshold. Oh, but be careful. In one case, it's smaller or equal, and in other case, it's strictly larger, because yeah, you cannot have in both cases that they may be equal. EB over 2 under square root. Now this is how we perform detection. We just compare with specific threshold, and depending what we see, we do we choose one of options. Okay, this is what we do. Let's see what we have next. Then we go to E. We need to sketch the conditional probability density function. And we come to conditional probability density function. So we have conditional probability density function y1 taking into account that we transmit signal S1 of x, and also we have another conditional probability function y1 okay, I forget this word, but we say that if we transmit S2, how y1 will look like? What will be the distribution of y1 of x? So now we need to specify these two conditional probability density functions. And what else? Okay, no, yeah, we just need to show. And we're coming back to, I think it was a question of material that we need to take into account noise. And now we're going to take into account noise, because without noise, the story is very boring. Yeah, I can tell you the story without noise, but you see that it's not interesting. Probably actually you always have to start story without noise. So, and now we have two axes, because second axis will be our probability density function. So it will be x for density of probability. For x-axis, we have what do we have? We have y1, so we have output value, output voltage. We have 0. Let's say that we have this is our value 2. Actually, maybe I should take one larger interval like this. This is no, now it's too large. This is fine. It was 2EB under square root. 2EB under square root. And without noise, actually what happens with your probability density function, you will have delta peaks. We have two delta peaks. One delta peak corresponds to transmission of signal S1, another delta peak to transmission of S2. Without any noise, you don't have any spreading. You have just perfect delta pulse. And this situation called as probability mass function. But it's unfortunately it's not our case, because as it was introduced, we also have noise, and due to this noise, you will get spread of this delta pulses. There is question: is this from Gaurav? Is the same threshold detection that we use in PCM detection? So I forget what is PCM. If you remind me what is PCM, I can try to answer. But in general, I mean, yeah, I mean, this threshold used widely. This is just the middle between two possible values. And I mean, probably not only in PCM, but in most of digital schemes, pulse code modulation. Maybe. I still don't remember pulse code modulation. I mean, of course, I remember these different schemes, but sometimes I have difficult to just connecting the name with what actually would happen. But anyway, yeah, this is very simple idea. So probably, yes, probably it's true. So let's go back to our problem. And as I said, this is what we have in ideal case when you have two symbols without any noise. You just get your distribution will be represented by two delta pulses. But when you add noise, as I said, you get spreading. So instead of one value, you will get the whole range of possible values. So I show with this green curve. This is a bell-shaped function that corresponds to Gaussian distribution. And this, I show all possible voltages that you get when you transmit signal S1. Because you transmit your symbol, and when you transmit symbol S1 at the receiver side, you get 0. But because of noise, you get spreading. And noise may have values positive, negative, it's all possible, and they have specific distribution, Gaussian distribution, and then we have to plot Gaussian distribution on this diagram. And also, the same happens when you transmit signal S2. When you transmit signal S2, you receive not only, of course, you receive value of 2EB under square root, but in addition to this value, you get additional disturbance that might have positive voltage, might have negative voltage. And for this reason, you also get the specific distribution of possible voltages that you observe at the output. And then I show with this purple color this range of possible voltages. So, and now we can say that this green curve is nothing else as our conditional probability density function of what we can observe at the output. So it's probability density function of y1, taking into account that we're transmitting signal S1. And purple curve corresponds to probability density function of y1, taking into account that we transmit S2. So these are two conditional probability density functions. How can we specify? What else we need to specify on this diagram? We also have to specify what's the variance. What's the variance? Actually, we have to specify. I mean, yeah, variance characterizes this probability density function, but on the plot, we have to specify standard deviation, which is square root from variance. Because remember, if you have units, let's say voltages, variance will be will have units voltage square. Yeah, but here we have to specify voltages, and we say that this width of distribution characterized by standard deviation sigma m, which is nothing else as n odd over 2 under square root. It is not probability density, it's not power spectrum density anymore, it is variance. And please, I would recommend you to check our previous stuff that we have shown that after resection, white noise become white limited with variance and not over 2. And of course, if variance equals to not over 2, then the standard deviation will be square root from n not over 2. And this is what I have shown here. Okay, also I can specify that B0 equals to 0. It's our green curve, and then another curve is B0 equals to 1. Also, what we need to specify and what we're going to use next is that we need to specify again where is the threshold. Actually it should be exactly in the middle, but on this spot it's slightly shifted, but theoretically it's right in the middle between two possible mean values. This is our middle, let's say, and the value for this point is EB over 2 under square root is our threshold. Also, we say what's the D mean. D mean, this is our minimum distance. And next, we're going to also calculate, we're going to show and we're going to calculate what's the probability of bit error. And there I will have to find, yeah, actually before we come to probability of error, we should talk about when actually, or why it happens that we have errors. What's the reason for this? And this picture also helps us to understand the reason for getting errors during transmission. So if you look, so again, I want to point your attention, draw your attention to the fact that we have threshold. And if whatever we get, whatever voltage will be above threshold, we say that we get, we received the bit B0 equals to 1. And if whatever voltage will be below 0, we say that it was transmission of bit 0. So very simple algorithm. But then what happens if we were transmitting signal S1, which corresponds to 0 bit, but we had very strong noise during transmission. It was so strong such that voltage after processing exceed the threshold. So, and you see that there is no zero probability that it may happen, that we transmitted signal B0 equals to 0, but due to very strong noise, our resulting value exceed threshold. And what happens? Happens the following. We made decisions that signal S2 was transmitted. Yeah, we say that it was transmission of S2, while in reality it was transmission of S1. And what we get error, that we get wrong decision. And how can we calculate what's the probability of error? And we can simply calculate what's the probability that our value exceed threshold. And we can use for this, we can use information about probability density function. And we need to calculate integral under the curve after threshold. And this value will give us information about the probability of error when we transmit S1, but we receive S2. And also we can get similar situations that when we transmit S2, but due to noise, we made the decision that it was received S1. So yellow region, we call this, if we calculate integral, the resulting probability we call as probability of bit error when we transmit S1. And the blue region we call as probability of error when we transmit S2. So we have two errors. S2. We have two errors. And let me actually check, because I already start talking about the stuff, but we should check actually what they're asking us about. So sketch conditional probability density function. So we did it. We have probability density function, conditional probability density functions. We have specified important parameters. So you see that there are many important parameters. There are these bell-shaped functions. There are variance, threshold, possible what's the values of bits. So which conditional probability density function correspond to which curve? Where is the minimum distance? All these parameters important. And now we go to part F. We need to specify the integral expression of the bit error rate as a function of the mean. But before we do this, actually, I would like also to write one more expression. I would like to write how the received signal looks like. So, taking into account that we have noise, then we go to part F, and we start and we complete discussion about probability of error, bit error. So we have y1 equals to integral from 0 to EB, and then I have my signal 2EB times Bn times psi 1 of t, psi n of t. So this is why we have transmission of signal, and also we have noise. And then we calculate correlation with the reference signal. So, and NT, white noise, it is white, with power spectral density equals to N0 over 2. But then if we open parentheses and separate this expression for two integrals, actually I write directly that for first integral we get result 2EB under square root times Bn plus last integral from 0 to TB and t times pi 1 of t. So simply speaking, I will say that the whole part, the second part, it will be noise. It will be some kind of noise after transformation. And previously we have shown that this noise will be Gaussian if original noise was white Gaussian. After processing, this noise will be also Gaussian with zero mean and variance N0 over 2. So I will say that instead of the whole part or the whole expression, we can rewrite as 2EB under square root times Bn plus some equivalent or effective noise. And yeah, and you see that actually this is what we have shown on the diagram above, that depending on what we transmit, we have different mean value, and then this mean value will be we have probability that we will go away from this mean value as and this probability high for small disturbances and relatively low for high disturbances. And this is what we get for this Gaussian distribution. Okay, this was just explanation. I should probably also write that this situation with this noise corresponds to special case. This is special case when we have normalized basis function. So integral from 0 to TB of basis function squared equals to 1. Then variance of noise after correlation will be N0 over 2. Variance of noise after correlation, sigma n squared equals to N0 over 2. This is a special case. Now we can continue, and we go to part where we need to specify integral expression of the bit error rate of probability of bit error. So we need to find integral for probability of bit error. And we need to, I want to remind you that how we calculate probability of bit error. Actually, we're doing the following. We calculate, or we need to know what's the probability of transmission of first signal, S1, and then we calculate what's the probability that we making error. While we transmit signal S1. So it simply means that we make decision that it was S2 while we transmit S1. Plus, second term, probability of transmission of S2 plus probability of error when we transmit S2. And in our case, probability of S1 and probability of S2 is the same, and it equals to 1/2. And also because we have chosen threshold in the middle, we have chosen threshold right in between amplitude of S1 and amplitude of S2. For this case, these two quantities will be equal for this specific case. And as a result, we can say that probability of bit error can be written simply as either probability of bit error when we transmit signal S1 or as probability of bit error when we transmit S2. This is what we can do for this specific case. Only for this specific case, when probability of S1 equals to probability of S2 equals to 1/2, and threshold in the middle. If these two conditions satisfied, then you can just use this simplified version. And as a result, what we need to do to calculate probability of bit error? We need to either calculate yellow area or calculate area of blue region, yeah, depending which one is better or easier to calculate. And we're going to use actually the following tricks because, as you remember, Gaussian function is, you cannot calculate integral of Gaussian function, and for this reason you have tabulated or tables of values for integral of Gaussian function. For example, error function or Laplace. Error function or Laplace function, they represent tabulated functions of integral for Gaussian function. So in our course, we're using error function, and I write it in the following way. We say that the error function of x is nothing else as 1/π under square root times integral from -x to x of exponential my exponential function minus t squared times dt, and it can be written also as 2/π under square root times integral from 0 to x exponential minus t squared dt. Okay. First option, but for us it will be more convenient to use so-called complementary error function. It is nothing else as 1 minus error function. Error function complementary of x, which is 1 minus error function of x, and it can be found as 2/π under square root integral from x to infinity and the exponential function minus t squared dt. So we need to represent integral in terms of error function to say to find probability of bit error analytically. Okay, are there any questions? answer any questions. But actually, we need this part, I think, for we have F. We need this part for J, but it's not that we have written here. So now let's start writing integral for probability of bit error. What we know about our, I would propose to choose a yellow region to calculate probability of bit error, because it will correspond, it will be easier to match it to a complementary error function. Because if you choose yellow region, then you start from a specific threshold, EB over 2 under square root, and then you have to calculate integral for upper limit plus infinity. And then if you look to this complementary error function, this is exactly what we have in our integral. So it's calculate integral from x to plus infinity. For this reason, I would propose you to choose yellow region. But if you choose blue region, you will get exactly the same answer. So there will not be any difference, but the derivation itself will be slightly more tricky, but just slightly. Okay, so what we are doing, we need to calculate probability of bit error when we transmit S1. And what are we going to do? We're going to write how we need to specify this probability density function, and then we say that we need to calculate integral from EB over 2 to plus infinity. So we just need to formalize this area of this yellow area. So we need to calculate integral from EB over 2 under square root to plus infinity of what? Of probability density function. And then we just need to write probability density function, just a regular one, 2 pi, and remember that we have square root of 2 pi times variance. And in our case, variance will be n0 over 2. Then we put square root of it times exponential function of what? Of do we write it in terms of y1 or do we write it in terms of x? I think we just use it as x, just as variable. X, and then yeah, we have mean value equals to 0. So we have x minus 0 squared divided by 2 times variance, 2 times n0 over 2. So I just use all what I know, and I specify this probability density function, and I say that we have to calculate integral from threshold to plus infinity times dx. Okay, and this is y1 b not equals to 0. Okay, fine. And as a problem, oh, wait a second. Specify the expression of the bit error rate as function of t mean. We have to specify as function of t mean. Just one moment, because does it make sense? Okay, we can just because I mean, if you need to somehow introduce d mean as it's written in the task to this expression, then actually we have only one place where we can introduce d mean, And this is the lower limit of our integral. Only there we have energy of average energy per bit, and only there you can somehow introduce d-mean. And I would like to remind you that d-mean can be written as 2EB under square root. And EB over 2 under square root corresponds to the mean over 2. So this is half of minimum distance. So, and as a result, you can simply replace lower limit by d mean over 2, and this is equal to the integral expression of probability of bit error as function of d mean. But actually, it will be more interesting when we write this expression in terms of error function, which is actually written in part J. I write here that we start part J, but actually we just continue the previous step. So we need to specify as error complementary error function. So we need to write this integral in form that's given above inside box. We have to somehow represent it in this form, integral we have below, and write it in terms of error function. So what's the problem? We have as expression for error, complementary error function, we have a variable t squared and nothing else. No any constants, nothing. And then you have also in front of expression 2 over pi. So, and now we need to modify our algorithm, or not algorithm, but our integral in order to match this representation. And I will do the following. I make the following replacement. I say that x squared over a naught, it will be my new variable t squared. And I can just calculate square root of it, and I get that x divided by a naught equals to t. Then I can calculate the derivative, and I get that dx divided by a naught under square root equals to dt. And final step, I need to understand what happens with limits, and lower limit for x was 2EB over 2. And after replacement, I get that if I substitute x in the expression on the left side, I have to divide by square root of a naught. Oh, 1 second, there's something wrong. It's EB over it's EB over 2. It's EB over 2, and the corresponding limit for t will be EB over 2 n, and the whole expression under square root. And when x goes to plus infinity, t also goes to plus infinity. So I need to do these replacements. Let me put box around these expressions. So, and let's continue. So now we can write that, or no, we can modify our integral. I can just write equals and continue below. What do we have? So we actually have the following. I will also, no, I just write we have integral from EB over 2 naught under square root to plus infinity. Then I have 1 over pi naught under square root times exponential function minus t squared. And also I have Yeah, it comes from there. When I replace dx by dt, I also have to multiply by a naught under square root. So, and now what we see, we can cancel a naught, and also we can multiply by 2, numerator and denominator, and we can represent our function as complementary error function. So we have 1 over 2 times integral from EB over 2 naught to plus infinity, 2 divided by E under square root times exponential function minus t squared times dt, and that's it. If you look to definition for complementary error function, it's exactly this formula that we have below, but of course except 1 over 2. So this part corresponds to complementary error function of EB 2 naught under square root. Yeah, this is a lower limit. And we can write that it equals to 1 over 2 complementary error function EB divided by 2 naught under square root, and that's all. So this is the resulting probability of bit error, in terms of average energy per bit and variance of noise. What was the question actually? Yeah, this was exactly the question. But we can also, we have this expression, but you can also write this expression, just do one more step and write it as function of d mean. Just remember that for d mean, we need to replace EB over 2 by d mean over 2. So, and we get it. We have 1 over 2 error, complementary error function, d mean over 2, and times square root of n. You can also sometimes you can see this in terms of d mean, minimum distance. So, yeah, that's all. As a homework, you can try to derive this probability of bit error starting with blue region. If you just write what the probability of getting in the blue region, and then try to represent it as complementary error function, it should be a good exercise. And I promise you that in the end you have to get exactly the same expression as we get now. Okay, are there any questions? Are there any questions, any comments? Okay.
A small doubt.
Yes.
You have taken orthonormal basis function in this case. So I couldn't understand why that basis function was actually orthonormal in this way.
Well, I mean, if you have only one function, it will be always orthogonal because it's only one. But why it's orthonormal?
Yeah.
Because energy equals to 1. Energy equals to 1. Because if you look to original basis function that we had in the beginning here, this is our basis function. And what it is? It is simply a rectangular pulse,
Okay.
duration TB, and amplitude 1 over TB under square root. And when you calculate energy, what you are doing, you're integrating from 0 to TB of basis function squared dt. And what it is, you just take amplitude squared 1 over TB times duration. I mean, if I just if I write what is the result of integral for this rectangular function times duration TB, and this result equals to 1. So this basis function has unit energy. But I mean, yes, we have only one basis function. But remember that when we're doing Gram-Schmidt orthogonalization procedure, we say that first basis function or like first signal equals to first basis function. And even if you have only one basis function, it is fine. If you normalize, and if but it's only one basis function, we still call this function as orthonormal. I mean, yeah, it might not make sense to do it because we have only one, but because it satisfies the conditions that it has unit energy and that it is, you call it as a basis function, then yeah, this is just formality. Okay, yes, any other questions? We still have some subtasks to go, but yeah. But we have slightly different focus after subtask J. Okay, let's go further. Now we assume the transmission of a continuous bit stream.
Professor?
Yes. What's the question? Yes, I can hear you.
I'm sorry. Like I didn't understand like the step where we pass from the probability bit, like we were describing in a normal distribution, and then we pass to the error function. I didn't understand how we like perform these substitutions and things. Can you explain again the G point, please?
I mean, idea is very simple. You have this integral here. This is the integral. This is, you just simply take probability density function, and you need to calculate. I mean, if you have probability density function, area under this probability density function will give you probability that you get value that corresponds to this area. Has it? We want to find what's the probability that we will be in this yellow region. And then what you need to do, you need to find area of this region. I mean, very simple, a very simple idea. You have curve, you need to find the area under this curve, and this area will correspond to probability. But the problem starts at the moment when we realize that we are working with Gaussian probability density function. And what's the problem? You cannot calculate analytically integral of Gaussian probability density function. It's not possible. At least most of scientists agree that it's not possible. And there are different ways how to overcome this problem. You can use different approximations of Gaussian function, polynomial approximation, or something else, or you can use tabulated functions. So the functions will pre-computed numerically, and results will store it in tables. And you can use these tables of results for specific functions, to calculate what is the result of this integral. And one of these such tabulated functions that pre-computed before is so-called error function complementary, or simply error function, because it's error function. This is just named for table of numbers. You have different tables, one table called as Laplace function, another table called as error function. This is just name of the table. And we can use this table to calculate our integral. Of course, numerically, not analytically. And in order to do this, we need to rewrite our integral in such a way that will correspond to definition of error function. And this is why I do this step. I just write my, where was it? Here, this is my original integral. Then I just start to change shape of this integral such that it will match definition of error function. And here, I do these replacements, and I see that actually this form, as it's written here, is exactly the same as definition for this tabulated function, which is one of this tabulate function error, which corresponds to one of many different tabulated functions, more specifically error function. And that's it. I just, instead of definition, I just write this shortcut, short notation, error function complementary. Yeah, we even don't use error function itself, but we use complementary function for it. Yeah, this is how we get, this is, yeah, because we don't have analytical solution, but here I say, please take table of numbers that correspond to complementary error function and substitute value that you have for EB over 2 and not not substitute, but and give me the value of function that corresponds to argument of EB over 2 and not under square. So you calculate this value, EB over 2 and not under square root, you get some number. You go to book that correspond to this table, you find this value in this book, and you get information what will be the result of function for this argument. This is actually what happens. This is what MATLAB doing. For example, if you will call complementary error function. Okay, yeah, I hope. Yeah, please let me know if it makes sense.
No, now it makes sense. Thank you, Professor.
Professor, I have one doubt.
Yes, please.
In the F part, so we have this probability of b comma s1. So in that we are taking integral from square root of eb by 2 to infinity. But our point of interest is from square root of eb by 2 to square root of 2 eb, right? So this is the area that we are calculating.
No. We're going to plus infinity because we have wide Gaussian noise. And I mean, maybe it's because I have shown, but I mean, when you have probabilistic function, it goes, I mean, officially, or like from mathematical point of view, Gaussian probability goes from minus infinity to plus infinity. Even take into account that probability that you get the value outside plus minus 3 sigma is very small. But from theoretical point of view, it's still non-zero. You have very small probability, but not zero. For this reason, okay, I can agree with you that in technical or engineering point of view, probably it will make sense just to limit yourself by, let's say, range 10 sigma, and then just don't go beyond because it never happens. But from theoretical point of view, when you write integral, we, instead of putting upper limit, we have infinity. But it's also help us to distinguish between yellow region and blue region, because for blue region we have lower limit minus infinity. For yellow region we have upper limit plus infinity.
Okay.
But from, again, engineering point of view, you can just maybe even limit yourself by 5 sigma. Just integrate from minus 5 sigma plus 5 sigma. And then 99% of all cases will be in this range. 99.99, I would say.
Okay, yeah. So in the other way, if you also think of the threshold that we are doing, square root of 2 EB. So after that, so I think
threshold is EB over 2, understood.
Oh, sorry. Okay, yeah. Okay, yeah, understood. Yeah, thanks.
But what was the question?
Actually, if we go after square root of 2 times EB, so we don't even consider the values. Right, because that's the max that we have. When we have B naught is equal to 1, it will be square root of 2 times EB.
But 2 EB under square root is not the maximum voltage that you might observe. This is the case that without noise, yes, you have two values. You have 0 and 2 EB under square root. Or you have 1 point, another point, without noise. But then you say that you have also, beside transmit signal, you have disturbing your transmission noise. And this noise has no any limit on the value of your voltage. Again, your noise might have voltage 1,000 million times higher than 2 EB under square root. But you also say that it happened, but probability for this event is negligibly small. Maybe it will happen only 1 times in million years. But from theoretical point of view, it is possible situation with very small probability. And for this reason, when we have noise in our transmission, we don't have such nice limits anymore, 0 and 2 EB under square root. When we have noise, our range of possible values will be continuous. We might receive any number in the range from minus infinity to plus infinity. Again, from theoretical point of view, because noise might have any possible amplitudes, because it's noise, we don't know. But what we can say, we can characterize this noise by probability. And we can say that most of values will be in the range. You remember that if you take plus minus 3 sigma, then the probability to be in this range will be 99.72 of all percentage of all cases. And that when you have noise, then you might exceed this value of 2 EB under square root. Did I understand right your question?
Yes, right, yes. It makes sense now. Thank you.
Okay, yes, other questions? Okay, so let's go to part H. Part H, and there we say that we assume transmission of continuous bit stream, Bn, and we need to find the mean transmit power, capital P, which is UTX squared. This is mean squared voltage. Mean squared voltage. Yeah, we calculate square value of voltage, and then we calculate mean of it. So, and this is actually just the same task that we solved for correlation theory of stochastic signals. Yeah, and we did it many times. So, when what actually happens is, sorry for this confusion, but we have capital P for, okay, for probability of error, we have capital B subscript B, but for power, we have just capital B. And I say that we have, what's the power? Assume that we transmit only, we can even consider only one interval. And for example, we transmit bit equals to 0. And I ask you what's the power during this transmission? Not average, but if you transmit bit equals to 0, and what is the power? And you answer that power equals to 0. Yes, Vivek, you're right. Bit equals to 0. And also Nandish, yeah. I mean, because we didn't transmit anything. And if we transmit bit equals to 1, then we have this rectangular pulse, which is scaled by 2 EB. Yeah, and when we calculate square value of it, we get that the power will be 2 EB. Yeah, this is the power when we transmit the bit equals to 1. And when what will be the average? You just take probability that you observe bit equals to 0 times probability plus probability of that you observe bit equals to 1 times the corresponding value of power. And this is how we get this average power. So this probabilities doesn't change, so we just take yeah, it will be really confusing if I start writing probabilities and power together. But yeah, this is first coefficient is probability 1/2 times value of power will be 0 plus 1/2 times power for Bn equals to 1. And we get that average power will be EB. So average energy per bit. Yeah, somehow it's confusing. Okay, next time I can check because we have implicit normalizations here. So it's not power itself, but of course it's normalized. It's normalized, it's implicitly normalized because we have, if you look to our basis function, amplitude of basis function depends on duration. Now you already have, amplitude itself, EB divided by time. And for this reason, when we calculate the power, we don't have, we divide by duration of signal. And for this reason, when we calculate power, we get that it equals to energy. But yeah, it's implicitly normalized by duration, of course, of basis function that we have. So for this reason, watts not equal to joules. So just keep this in mind. Okay, H. But from formal point of view, you get that yes, power equals to EB. So let's go further. And now then we need to draw the energy spectral density. Psi1 F. And yeah, and actually we're going to start trying to find correlation of the transmit signal. So, I need to find energy spectral density of basis function, and the easiest path will be to take our basis function as it is, calculate Fourier transform of basis function, then we calculate absolute value squared for spectrum of our basis function, and this is nothing else as our energy spectral density. So this is the path that we're going to take to find energy spectral density. And I just want to remind you that our basis function itself is a rectangular pulse. From 0 to TB, it is amplitude 1/TB under squared. So this is our basis function. And yeah, we can say that psi1 of t equals to 1/TB under square root times rectangular pulse t minus TB/2 divided by TB. This is our original function. We calculate Fourier transform. We get psi1 of f equals to 1/TB under square root times TB times psi function, psi, not sine, pi f TB times exponential term for shift of each frequency component. Exponential minus j to pi f TB/2. Then we calculate psi1 of f absolute value squared, and we get that we have, of course, we cancel TB, And after we calculate square value, we get TB times psi squared pi f TB. And we don't have exponential part because it will be cancelled when we calculate conjugate and multiply. And we get power spectral density, energy spectral density. Sorry, it's energy spectral density. TB times psi squared pi f TB. So you see that actually energy spectral density doesn't depend on shift in time domain. You can shift your signal in time domain as you want. Energy spectral density will be the same. It doesn't influence energy spectral density. Shift in time domain. Okay, then that's all for part I. Then we go to part J. Find the discrete autocorrelation function phi pp of m, which is equal to expected value between sequence, original sequence, and shifted copy of the bit sequence b of m. Yeah, this is very traditional for what we discussed. Nandish reminds that we also have to draw. Do we? Yes, draw the energy spectral. Thank you, Nandish. Thank you. Okay, so, but yeah, of course, you also can do this. It's not difficult. So, one over TB, 2 over TB, and so on. A maximum value will be TB, and then we show that it is psi square function. It is smooth function, so no sharp edges. Everything is smooth. Approximately, we show it, and it is continuous. Of course. This is frequency domain. This frequency domain is our pi psi 1 f, and that's how it looks like. Okay, now we can go to part J. Find the autocorrelation function. So we need to find autocorrelation function of our bit stream as index of shift in indexes, Pn times Pn plus m. And we can write this autocorrelation function. Of course, as far as adjacent bits independent, we simply calculate second moment when shift between original and copied sequence equals to 0, and it equals to first moment squared when this shift is non-zero. We have such traditional definition for autocorrelation function, and if we just plug all what we know, we get 1 over 2 for m equals to 0, and we get 1 over 4 for m non-equal to 0. Why? Because second moment will be the following: 1 over 2 times 1 plus 1 over 2 times 0, and equals to 1 over 2. And for first moment, it will be 1 over 2 times 1 plus 1 over 2 times 0 squared. So if 1 over 2 squared, it will be 1 over 4. This is the reason why we get such values. So this is what we get for autocorrelation of bit stream. Then we go to next J, K. We go to K, and there we say that in lecture it will be shown that the autocorrelation function of sample signal can be found by just taking discrete autocorrelation function and normalize it by duration, by symbol duration, but in our case, symbol duration is the same as bit duration. And yeah, we already did it before. And here we just needed to do it again. And we get the following. We get the following, that I can actually write directly what will be the result. X pi x delta equals to, this is what we have. We have value at 0. Okay, I need to plot it, otherwise it's not clear. After we calculate this discrete autocorrelation function, we get phi dB of m, function of index. And what we have? We have that at 0, we have discrete index 1/2. And then we have for all other values, shifts, we have 1/4. And this shifts even in integer values. Then when you find the corresponding autocorrelation function in time domain, in delay domain, you simply take the same shape, but you normalize its discrete pulse and convert it to a Dirac delta pulse. Now we have along x-axis, we have delay, tau, continuous delay, and instead of discrete delta pulses, we have Dirac delta pulses, which are normalized by TB. So we have 0, TB, 2 TB, and so on. Minus TB, minus 2 TB. And magnitudes at 0, we have 1/2 TB. And for all others, we have 1/4 TB. So this is our autocorrelation, psi delta, tau. Okay. And we can write analytically how it will look like. In order to do this, I just need to split delta pulse at 0 for 2 parts. And I can write that delta, the autocorrelation function equals to 1/4 TB delta 0 plus summation, n goes from -infinity to infinity, 1/4 TB times delta tau minus n TB. I can write it in this way. Oh, right. So this is our autocorrelation function, and finally, we need to find power spectral density. So for power spectral density, simply need to calculate Fourier transform of the functions we have found here. So we just calculate y x delta f. Calculating Fourier transform for delta pulse, it will be constant. 1/TB, 4TB, plus, and then we have Fourier transform of sequence of delta pulses. And if we do this, we get another sequence of delta pulses. We have 1/4TB times 1/TB times summation mu goes from -infinity to infinity. Delta pulse f minus mu times 1/TB. This is Fourier transform for sequence of delta pulses. Do we need to do anything else? Sketch. Okay, we have sketch for correlation function. And we need to sketch. Okay, let's also sketch this part. Okay, Akash asking about magnitude of component at 0. No, at 0 we don't have 1/4 TB. Why? Because actually we also have we split this part. We have component at 0 for two parts. Because look, we have a sequence of delta pulses that defined by summation, and mu equals to 0 also part of it. Yeah, if you substitute mu equals to 0, oh, not here, but above. Mu equals to 0, then you get that you have result 1/4 TB delta 0, and another 0 comes from summation 1/4 TB delta 0. And if you calculate this summation of two parts, you get 1/2 TB. And this is exactly what we have for the whole part there. One part will be inside summation, and 1/2 will be as it is, just separately. This is the idea. Okay, so I mean, it's not difficult to plot. It's not difficult at all. We simply have constant level, 1/TB, sorry, 1/4 TB. And we have a sequence of delta pulses spacing 1/TB. Plus with minus, and magnitude 1/4 TB squared. This is our fast density. So get. And final step is part L. We have completed today. So next time we can start with a new task. We say that our transmit signal can be represented as convolution between 2EB under square root times basis function with sequence of bits that we transmit, x delta t. And what we need to find fast packet density of this sequence of signal UTX. And of course, you remember that if you have convolution in time domain, in frequency domain, we can simply replace it by product. And here we can even simplify further, write it as 2EB times energy spectral density pi psi1 f times power spectral density phi x delta f. Now we just need to calculate the product. And we already know what is energy spectral density, it's given above, and what is power spectral density of x delta, it's also given here. You just need to combine these two parts. And if we do this, actually what you should keep in mind is that we have, for power spectral density, we have two parts. We have constant level and we have sequence of delta pulses. So as a result, your resulting plot will also contain two parts, which is product between constant and chi-square function plus discrete sequence of delta pulses times chi-square function. So let's plot directly the result, and we complete our tutorial today. So 1, 2, 3, 1, 2, 3, 0, 1/TB, 2, 3, and so on. Okay, and this is so what can we do? We just start with constant level. For original function, it was TB, for energy spectral density, times here 1/4 TB times 2 EB. As a result, maximum value will be EB over 2 and we have chi-square function. Chi-square function, this is constant part. And another part, we have sequence of discrete pulses times chi-square function again. But look, we have interesting. Okay, I try to zoom it out so that you can see both of them. We have interesting result. Look, that we have every that location of delta pulses match the location of zeros of chi-square function. As a result, they cancel each other. So not cancel, but the product will be equal to 0. And what we get only one delta pulse at origin left after this product. And what's the magnitude of this delta pulse? It will be TB times 1/4 TB squared times 2 EB. Yeah, and I can show that besides this chi-square function, we have delta pulse at origin with magnitude of EB over 2 TB, I believe. In the sketch of the past tests, the DC level is higher than the impulses. I mean, remember that impulses, I mean, it's, of course, it depends on, for discrete case, it depends on values. Yeah, but for continuous case, remember that impulses, they have infinite amplitude. They go to plus infinity. But area under pulse will be equal to constant value. That amplitude isn't infinite. For this reason, it's not correct to say that it's not very, yeah, it's not good to say that impulses below DC level or DC level above, because impulses, they just go to plus infinity or minus infinity. Yeah, I hope it's clear. We just need to denote somewhere that it is arrow, that it's delta pulse, and it goes to plus infinity, but it has finite area under the curve. Yeah. So, and we get that we have these two parts, continuous part, and we have delta pulse, this magnitude EB over 2 TB. And we can finally, write expression. So we have chi-square function, we have EB over 2 chi-square function phi at EB plus delta pulse at 0 is magnitude EB over 2 EB, delta pulse 0. Of course, you can write it as product between chi-square function and sum of delta pulses, but you can simplify. You can just remove all these details because none of the delta pulses remain after this product, and only one will be there. So that's it. Are there any questions? Any comments? I hope I didn't forget any scalar. That's all for this task. Okay. If not, then thank you for your attention, and we see each other again online about next week. I wish you productive rest of the week and see you next time. Thank you and goodbye. And if you still have some questions, please let me know. You're welcome to write in the chat or let me know through email. It's not a problem.